Okay, we'll be going over a bunch of related rate questions, and you guys can also go to the description because I will have the link to the file of all these questions for you guys. These questions, they are hard, but as long as you guys practice them, you can do them too. This is the first one that we have. Right here it says, when the circular metal plate is heated in an oven, its radius increases at the rate of 0.02 centimeter per minute. We would like to know at what rate is the plate's area increasing when the radius is 60 centimeters. Right, this is how I will demonstrate the situation for you guys. I will draw two pictures for you guys. As we can see, here we have a circular plate, and of course we care about its radius, so I draw this right here for you guys. And then after a while, as we all know, this plate is going to get bigger because it's being heating up. So I'll just draw a bigger circle right here. And as you guys can see, not only the area is getting bigger, but also the radius is getting longer. So be sure you know that we have two things that are changing in this question, namely the radius and also the area. The radius and the area, they are both functions of time in this situation. And I will go back here, I'll indicate the following. Right here it says, we are given that the radius increases at the rate of 0.02 centimeter per minute. This is telling me we have dr dt, and that's equal to 0.02. Whenever you see the rate in the related rate questions, that's pretty much the derivative. And you can just put on d whatever over dt, like that. So this is the given information, and then we are trying to find the rate that the plate's area is increasing. So what do we want? Let's use the derivative notation. Well, it says the rate, so we put on d, and then we have the area, so let's put on a. We want to have dA dt, right? Very good. All right, now this is how we organize the information. And actually, lastly, it says when the radius is 60 centimeters. So that's actually right here at the instant that the r is equal to 60 centimeter. Because this is the original and it's been heating up and it's going to get to this point, and we'd like to know how big is the area changing, right? Okay, now this is what we need to do. We have to think about a formula that relates to the area and also the radius. Of course, we know the area of the circle is just pi r squared, so we can use that. Let me write down a is equal to pi r squared. This is the quantity equation, right? It gives you the actual area and also the actual radius. And in order for us to get to the rate equation, we just have to differentiate this equation with respect to time. That's it. So let's go ahead and do that. Let me put down d dt like this. You just have to remember both of the a and the r, they are functions of time. Therefore, on the left hand side, when you're differentiating a with respect to t, you get dA dt, alright? And then on the right hand side, pi is just a constant multiple with this, so pi pretty much stays. But r is also a function of time, so here we will have to use the good old power rule. Let me bring the 2 to the front, minus 1. So we will have first the 2r like this, and then because r is a function of time, and we use the chain rule, we multiply by dr dt like this. And now we have this equation relating to the rates. That's why it's called the relating rate. Anyway, now we're trying to find out dA dt, so I'll just keep this. And then 2 is just a 2, pi is just a pi, r we care about at this particular moment, so we just plug in 60 right here for r. And by the way, at different instant, you will have a different dA dt. So you really have to pay attention to the question right here. It says the radius is at 60 centimeter at that instant. So use this right here. And for the dr dt, the radius is increasing at the rate of 0.02, right? So that's the constant rate for the r. We just have to plug that in, 0.02. And that's pretty much it. And all we have to do next is just multiply things out. And usually we just multiply out the regular numbers and we leave the pi as how it is. I can just multiply 2 and 60, that's 120, and then times 0.02, we get 2.4. And of course, attach the pi. Lastly, dA dt, the unit for that is cm squared because we are measuring centimeter. So the area has cm squared for the unit. And the time unit is minutes, so we put on per minute. And with this, that's it. So I told you it's not that bad. Be sure you guys watch my other videos. You guys can get more practice with this. And at the moment, that's it. Okay, welcome back to another related rate question, and if you find my videos to be helpful, please leave a comment and let me know. Anyway, here we have this question. It says a water tank has the shape of an inverted, and this just means upside down, inverted circular cone. And we know that the base radius is 2 meters and the height is 4 meters. And right here it says if water is being pumped into the tank at a rate of 2 meter cube per minute, we would like to know the rate at which the water level is rising when the water is 3 meters deep. Okay, so as always, I will draw two pictures for you guys for the related rate questions. We will be drawing the water tank first, of course, and this is the cone. And first, you have to know that the radius of the cone is 2, and then the height right here is 4. And the water is being pumped in, and water should be in blue, so I will put down in blue. So like this, water will put down H2O if you're more of a chemistry person. Anyway, when you're putting water, we are going to keep track of how much water we have in the tank. So let's say we have this part right here. And as time goes on, we know that the tank will actually stay the same, right? The tank is not going to get any bigger nor smaller. So let me try to see. They are the same size. I still have 2 and I still have 4, of course. But when we have more and more water goes in, we know that this part is going to be more and more, right? Higher and higher. So I'll just put down this right here for you guys, like that. So the blue part is the part that we want to focus on. Well, what are changing? It's first the radius of this cone formed by water. So I'll just call this the water cone. And then we also have the height of the water cone. Right? This right here are changing, and be sure you label them with variable. The things that are not changing, the constants right here, you can just put that down as numbers. Anyway, this is what we have. And now let's go back to the question and grab information. Well, we used the 2 and 4 right here already, so that's pretty much it. But it says the water is being pumped into the tank at a rate of 2 meter cube per minute. So here, let's write this down. This is telling us how much water is going to the tank. That's the volume. So I'll put down dV because it says we have the rate. dV dt is 2. And we are trying to find the rate at which the water level is rising. So let me just put this right here. And that's this part, that's the h, right? That's the height of the water. So what we want is the h dt, all right? And it says when the water is 3 meters deep or 3 meters high. So that means we want this part right here. So I'll just put down at the instant that h is equal to 3, right? Remember, this 4 in black, it's the whole thing. And we are looking for the part in blue, like that. Okay, for the related rate questions, we have to know a lot of geometry, especially the formulas for areas, volume, triangles, whatever, right? Here, we are talking about cone, and we are talking about how much water we have in the cone. Therefore, we have to use the volume formula, and I'll put this down right here for you guys. The volume of a cone is given by the formula 1/3 pi r squared times h. And in this video, I will just use the formula. Maybe later on I will explain why this is the formula for the volume of the cone, but that's later on. Anyway, let's identify what are the things that are changing. The volume of the water cone is of course changing. It's getting more and more water inside, right? And also the radius of the water cone. Originally it was like this, but it's going to get longer right here. So this is also changing. Lastly, h for the water cone, originally it was only this high, but now it's going to be this high. So this is also changing. Notice we have 1, 2, 3. We have 3 functions of time. That's not that good. But it's okay because this is what we can do. We can reduce one of the variables right here by looking at this picture again. Well, if you look back to here, this portion that we can see on the side, right here, right, this triangle, I'll put this down in black like this. We know that the top right here is 2, right? The base area right here is 2, and then the height right here, the whole thing is 4. And if you look at the water cone, we have this much only. This right here we labeled it to be R. This right here we labeled it to be H. Notice these two triangles are similar, so we can use a similar triangle, right? We can just like isolate, we can solve for one of the variables. You can do whichever way that you would like. You can do this over that, it's equal to this over that. Or you can do this over that, it's equal to this over that. Up to you. Let me just do this shorter side to the longer side in the triangle in black right here. That's equal to the shortest side to this side of blue, like that. And then we'll solve this real quick. That's just, see, this is 1/2. That's equal to R over H. And let's multiply both sides by H. We see that R is equal to 1/2 H. And that's pretty much it. And now let me plug this back to here, and then you will see we don't need to deal with R in this equation anymore. That's good. I hope R doesn't feel left out, but it's okay in this video. Anyway, right here, volume, and I'll just put on V, okay, because we are talking about the cone already. Here we have 1/3. Pi is still pi, but R, as we saw, it's just half of H. So let's put down half H like this. And then square, and then lastly we have the H. And then from here, let's just work out some algebra right here. V is still V. Here we have 1/3 pi, 1/2 square is 1/4, and H square is just H square, and we have H. And notice, everybody here, they are just multiplying. And I would recommend you guys to do the following. When you have a fraction, multiply them first, and then put it as a fraction, as a coefficient, all the way in the front. What do I mean is, 1 times 1 is 1, over 3 times 4 is 12. So I will put down 1/12 like this, all the way in the front. And then we have the pi, and then we have H squared times H, that's just H cubed, just like that. And now we can work with this equation. We can just differentiate this with respect to time, and then the left hand side give us the v dt, and the right hand side, this is just 1/12. Pi is just pi, and actually bring this to the front, do the power rule. So this is technically 3/12, and then we have the H square, and then we have the dH dt, because H is also a function of time. Alright, so this is of course 1/4, and I need to find out what dH dt is. We know dV dt is 2, so I'll put down 2. This is just 1/4, and then pi is pi. H is 3, so let's put that down, and square that, and then dH dt, we don't know. And now let's just work this out real quick. 2 equals 2. This is just 9 times 1/4. We have 9/4. Let me put a pi on the top right here, because now you see this is multiplying with dH dt. We can just multiply both sides by 4 over 9 pi. That's multiplied by 4 over 9 pi right here. So that this cancel out. And then we get dh dt equals to 4 times 2 is 8, over 9 pi is just 9 pi, and then we are pretty much done. But we have to answer this question carefully. We have dh dt, and you see this is a positive number. That means the water is increasing, right? The water is rising. And the unit for h in our case is meters, right? We are measuring meters. So the unit right here will be meters per minute, right? So we'll put down meters per minute. And this right here is it. Okay, another related rate question. Here we have a ladder 10 feet long races against the vertical wall, and it says if the bottom of the ladder slides away from the wall at a rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? Well, you know the deal. I will draw two pictures for you guys. First, this is the floor, and let's say this is my wall. And I will also draw the following. It says the ladder is 10 feet long, right? And during the whole process, the ladder is not going to be longer nor shorter. So I will just draw the ladder to be like this. Let's say this is 10. Okay, and it's always going to be 10 during the whole process. Therefore, I can just label the 10 right here, right away. And I will just show you guys what happens right here. Well, it says the bottom of the ladder is sliding away. So that means you are pulling this away, right? So you can imagine this is being pulled away and this is going to sliding down. Therefore, the next picture is going to look like this. This and that's supposed to be 10 and 10, alright? So just excuse my picture. Anyway, this is still 10. This is how we are going to do it. We have to label the things that are changing. We know that this distance and this distance, they are changing. This is the vertical distance. I will just label this as y. This is the horizontal distance. I will just label that to be x. And once again, during the process, you can see that this has gotten shorter and this has gotten longer. And we care about at the instant that it says the ladder is 6 feet away from the wall. This part, 6 feet away, so that means x is equal to 6. And now let's go back to the equation and pick up the things that we have. It says the bottom of the ladder slides away from the wall at a rate of 1 feet per second. The bottom, that's the x that we have right here, right? This right here tells us we have d what? dx. Good. dx dt equals to 1, right? And the question is asking us how fast is the top of the ladder sliding down. So let me just write this down right here. How fast is also asking for the rate, and in our labeling we want to know dy dt. Okay, so that's pretty much the information. And now let's look back to this picture and come up with an equation that relates to x, y, and 10. Well, this is nicely enough to be a right triangle, so of course we can use the Pythagorean theorem. Namely, this square plus that square is equal to this square. So write down x squared plus y squared equals to 10 squared. And pay attention to this. I put down 10 squared right away because I know this length is always 10. So I can just put down the 10 squared right away. I'm not going to plug in 6 right here yet, alright? This is later on when we have the rate equation already, and then we're trying to solve for the dy dt. This is later on because this is given the instant. But in terms of the equation that we have, you can plug in any constant right away, and then of course if they are changing, you keep them as variables. And now we can totally differentiate this now with respect to t. First, the derivative of x squared with respect to t is just 2x and dx dt. Next, we add it with the derivative of this is 2y and dy dt. Good. And what's the derivative of 10 squared? The answer to this is not 20. The answer to this is just 0, because this is just the derivative of 100. It's a constant 0, right? So that's pretty much it. And for the people who really want to just label this as like z squared, you realize you get 2z dz dt, but dz dt stays the same, so that's 0, right? dz dt is 0 because z stays the same. Anyway, this is it. Now you see that that's just plugging numbers. 2 is 2, and now I can divide everything by 2, but I'm not going to do that. It doesn't really matter. X is 6, so that's plugging 6 right here. And the x dt is given to be 1. And notice I label this as positive 1 because x is getting longer, right? X is getting longer. So this is positive 1 for dx dt. And then we add it with 2 is still 2. Y is, well, this is a quantity. When the instant that x is equal to 6, we actually need to find out what y is. And to do so, in fact, I have to rely on this equation for the quantity. So when x is 6, I plug into here. Let me figure this out. We have 6 squared, that's equal to, 6 squared plus y squared, that's equal to 10 squared. And then this is 36 plus y squared is equal to 100. And then minus 36 on both sides. Y squared is equal to 64. Take the positive square root, you just get y equals to 8, right? So y is equal to 8 when the moment that you have x equals to 6. And then with that, you can solve for dy dt. That's really nice. Let me keep this on the left hand side. Well, 2 times 8 is 16, so let me put on 16 dy dt. Bring this to the other side, that's going to be negative 12, and then divide both sides by 16. So let me just do that right here for you guys. Divide both sides by 16. The good old algebra days, right? Just cancel things out nicely and cute. Huh? Anyway, dy dt is equal to, you reduce this fraction, and you get negative 3/4. Right, that's pretty much it. But now we have to interpret our answer carefully. Dy dt is negative because this distance is getting smaller and smaller, right? Because it's sliding down. So y is getting smaller and smaller. That's why we have a negative rate. And depends on how you want to answer it. In my class, you can just label dy dt is equal to negative 3/4 and attach the unit, which is feet per second. This right here is okay. Or if you want to answer this properly, you just write it down in sentence. And you have to use the phrase sliding down, right? You can just say the top of the letter is sliding down at a rate of, and if you use the phrase sliding down, this includes a negative already, so you just say sliding down at the rate of positive 3/4. This right here should be a positive 3/4 feet per second, right? So depends on how you want to answer it. That's pretty much it. Okay, another related rates question. Here we have car A is traveling west at 50 miles per hour and car B is traveling north at 60 miles per hour. Both are headed toward the same intersection. So the situation is A is going toward the west and B is going toward the north. So they are going toward each other, right? And it says at what rate are the cars approaching each other when car A is 0.3 mile and car B is 0.4 mile away from the intersection. So as always, I will draw you guys two pictures. So suppose right here I have my roads, And of course, here it will be my intersection. And let's say car A is right here, which is going toward the west, and then car B is down here because it's going toward the north, right? Well, we know that because A is going toward the west, this distance here, and likewise car B is going up, which is this distance. And we would like to know how fast are the cars approaching each other, meaning the distance between them right here, alright? And as you guys can see in the next picture, we care about that instant when A is 0.3 and B is 0.4 miles away from the intersection. So I will label this for you guys. Because this is for car A, I will just label this as A. This is for car B, I will just label this as for car B. And this right here, when you have A, when you have B, of course, let's label this as C. In this situation, A, B, C, they are all changing. They are all functions of time. And in the next picture, you'll see A is closer to the intersection, and likewise B is also getting closer to the intersection. And the distance between them is also being shortened, right? So as you guys can see, you still have the ABC. I'll write down. We care about the moment at instant. A is 0.3 and B is 0.4. And of course, from this we can figure out C, but let's get back to this right here. So I will look at this again and grab information. Right here it says car is traveling 50 miles per hour. So this is telling me that I will have dA dt equals to 50 miles per hour. And right here, car B is traveling at 60 miles per hour. So I'll write it down as dB dt equals to 60 miles per hour. However, though, before we continue, remember A and B, they are going toward the same intersection. So the distance of A is actually getting shorter. Likewise, the distance of B is also getting shorter. So technically, this right here should have been negative 50 miles per hour. And right here, this should also have been a minus, right, negative 60 miles per hour, because the distance is getting shorter right here. All right, and we would like to know at what rate are the cars approaching each other. So this is telling us we want dc dt based on our labeling. Okay, so we can come back right here. We know here we have a right triangle. Of course, the famous a squared plus b squared equals to c squared. And notice I wrote down a, b, and c right here. This equation is with 3 variables because once again, they are all changing. They are all functions of time. I cannot plug in any numbers right here. Okay, you can only do so if you have any constant, just like the previous example. But right here, I will just keep it as a squared plus b squared is equal to c squared, and then differentiate this with respect to time. Right here, we'll get 2a dA dt, and then we add it with 2b, and we will have dB dt, and then this should be equal to 2c dc dt. So this is really, really nice. And again, you can divide everything by 2, but it's okay because most likely we can just use a calculator, so it doesn't really matter. I will just keep it as how it is. I think it's nicer, so you can see the 2's. I don't know. Anyway, I keep the 2 and then the a. We care about the instant when a is 0.3, so let's put that down. And the a dt, as we discussed it earlier, that should have been a negative 50. So I'll put down negative 50. And this right here is actually crucial. If, for example, maybe A is going toward the intersection, while B is going, if A is going away from the intersection, while B is going toward the intersection, then in that case, the A dt will be positive, and then the B dt will be negative. So you really have to pay attention if the rates are positive or negative. And if the distance are getting shorter, that's why we have the negative rate. All right, then we continue. plus 2, and then the b is 0.4. Let's put that down. And then dB dt is negative 60. So let's write that right here. And this is equal to 2 is 2. C, well, at the moment now when we have A and B right here, we also need to figure out what C is, and that's a quantity. I will have to plug into this quantity equation to help me out, right? So I will get 0.5 because it's 345. So, but I will show you guys the work anyway. Anyway, 0.3 square plus 0.4 square. That's equal to C squared, and then you can seriously just work this out. You will get 0.09 plus 0.16, which is 0.25 equals to C squared. Square root both sides and take the positive value. You get 0.5. Anyway, that's for C. And then you can just work this out, and then you have the dc dt right here. And the beauty of this is that look at this. 2 times 0.5 is just 1, so we have dc dt right away. So I didn't divide everything by 2. Oh, that was nice, huh? And then you can of course just use a calculator also, just like typing everything if you would like, and then seriously just work everything out, and you will end up with negative 78. Alright? So you can answer it in 2 ways. You can say dc dt is negative 78 and put on the units, which is miles per hour. I will just write this down right here. Miles per hour, like this. And you notice because the rate is negative, that means the distance is getting shorter and shorter. So you can also say the following: the cars are approaching at a rate of 78 miles per hour. And if you use the word approaching, you don't need to have the negative sign for the rate. And this is it. Hopefully this helps, and if you guys want to see more, be sure you guys check out the description for the link to the playlist and also to the file of the questions. And that's it. Okay, another related rates question. Here we have at noon. Ship A is 100 km west of ship B, and ship B is sailing south at 40 km per hour, and B is sailing north at 20 km per hour. How fast is the distance between them changing at 4 o'clock? Well, let's draw 2 pictures. First of all, it says A and B is pretty much 100 km apart, and that's at 12 o'clock, right? So my picture is just going to be like, suppose A is right here and B is right here, and the distance between them is 100. And also it says A is just sailing south while B is going up north. Therefore, the horizontal distance between them doesn't change. This is always that 100. The next picture is that it's going to be like this. Well, actually, let me put down, this is at 12 o'clock. All right, here is A, here is B, and the original distance between them is 100 kilometers. Now the next picture, which happens at 4 o'clock, let me also put that down right here. Well, B is going up, and I think B is going slower, so I will just draw like this. But the horizontal distance is the same, it's still 100. And let me say B is up here now. Okay, so it's this distance from here to here, and that's B. I'll just put B for the distance that ship B has traveled it so far. Similarly, we know actually B is like this only, but A, because it was going faster, so it will be more down here. I will just put this down right here. This is A, and I will just draw this right here. This is the distance that A has traveled down south, like this. Well, we also have to keep track of the distance between the ships. Originally, it was just this horizontal distance, but A goes down, B goes up, the distance between them becomes this. and also changes. It got longer compared to the earlier one. This right here, of course, when we have A and B, let's call the whole thing right here C. And let's go back here. Right here it says A is sailing south at 40 kilometers per hour. This will tell me dA dt equals to, because this distance is getting longer and longer, so I will put down a positive 40. Similarly, B is sailing north at 20 kilometers per hour. This will tell me dB dt is positive 20. And the question is asking us, how fast is the distance between the ships changing? So what we want is, based on our picture, I want to know the distance, how fast this is changing, which is dc dt, right? So that's pretty much how we organize all the informations. And now let's see if we can come up with any formulas or any equations to work with. This right here originally was just like a straight line, so cannot really do much. But at 4 o'clock, we see we have pretty much two of these triangles. But even better is that, notice this right here is 100. That means from here to here is still 100, right? And this right here is B. That means from here to here, it's also B. And if you look at this big triangle, that's just a right triangle, and then I will be able to come with a formula, one equation right here, based on the Pythagorean theorem. Well, be sure you know that this whole thing is A plus B. So we can get to work. Let me put down 100 squared. And because this 100 is always 100, so I can put down the 100 right away. And then add it with A plus, this should be a plus, I don't know, just put down plus like this. Okay, it's plus. Plus, I will just put down A plus B right here, square, and this is equal to C squared, like this. Okay, so that's the equation that we have. A, B, and C, they are all functions of time because they are all changing, except for the 100 right here, so that's why I put this down. That distance is 100. Anyway, we can look at this now and differentiate this with respect to time. The derivative of 100 squared is 0, that's nice. And then the derivative of this, I will bring the 2 to the front and then minus 1. And then I get 2, and then the inside stays, which is A plus B, and then to the first power. But the chain rule says we will have to multiply by the derivative of the inside. Derivative A is dA dt, and then we add it with the derivative of B, which is dB dt. So that's what we have. And on the right hand side, we can bring the 2 to the front, and then we have the C, and then we have the dC dt, like this. So this is our rate equation. And now we just have to figure out A and B. We are given the dA dt, dB dt already. We also need to figure out C, and then dC dt should be able to solve from the rest. Okay, now we have to do some more math right here. This time, we are given that at 4 o'clock, right? So that means the ships have been traveling for 4 hours, right? So I'll just indicate that this is after 4 hours. I need to figure out how long this distance is, which is the A value right here. Well, I'll put this down. A is equal to, remember, time times speed give us distance. Time times speed give us distance. So I just have to do 4 times 40, which is going to be 160. This distance at 4 o'clock is 160 kilometers. Similarly, we do B. It's also 4 hours times 20 only though, so let's put down 20. And then of course that's 80. Now we have the quantities a and b. We can plug in this back to the quantity equation, and then let's write this down. We will have 100 squared plus a and b is just this now, so we can plug in, which is 160, and plus b is 80, and then you square that, and then that will be c squared. Of course, now let me just take the square root on both sides, and then you can just enter everything right here on your calculator. And let me just tell you guys, after you work that out, you'll get c equals to 260. And now we can just bring everything right here. We will have 2. A is 160 plus b is 80. The ADT is positive 40, so let's put that down right here. And then the BDT is positive 20, so let's also put that down. And then 2 is 2, C is 260, so let's put that right here in this little parentheses. And then we have the dc dt. And then from here, you can just divide both sides by this guy. So I'll just divide 2 over 260, so they cancel. And then divide this side by 2, and then 260 right here, right? And of course, you can just use a calculator if you like, or you can do like mental math, whatever if you like. In the end, work this out and then just round your answer to 1 decimal place. You get 55.4. And this is a positive number because C is getting longer and longer. So dc dt is positive 54.5. And I'll write this down, kilometer per hour. And that's it. Okay, another related rates question. Here we have 2 sides of a triangle, and it doesn't have to be a right triangle. 2 sides are 5 meters and 8 meters in length, and the angle between them is increasing at a rate of 0.06 radians per second. We would like to know the rate at which the area of the triangle is increasing when the angle between the fixed sides is pi over 3 radians. Okay, so keep in mind, 5 and 8, they will always be 5 and 8 for the 2 sides. So let me just draw a picture right here for you guys first. Let me put on the longest side right here first, which is the 8 meters. And because this right here is always 8, that's why I label the 8 right away without labeling that as a variable. And then we have 5 meters, so I will just put on the 5 maybe like this, right? So this is 5 meters. And in order for us to make this into a triangle, of course, we have to connect with the endpoints right here. But in fact, we don't care about this side right here at all. I will tell you guys why in a second. Well, right here, the only thing that's changing in our situation is the angle between the fixed sides. And then it says this is getting bigger and bigger, so you can imagine this side is like opening bigger and bigger, right? We care about the moment that this angle is at pi over 3 radians. So I will draw another picture for you guys. So this is the 8, and then this side is going to be opening right here now, and this is still going to be 5. But the angle got increased like that. And of course, if you want to talk about a triangle, just connect the endpoints right here and right here. It says the 5 and 8, they are just constant, so okay, that's good. And the angle between them is increasing at a rate of 0.06 radians per second. This is telling me d theta dt is 0.06. And because this is changing, that's why I label this as a variable, right? Now we also want to find out the rate at which the area of the triangle is increasing. So what we want to find out is dA dt is equal to what? This is what we want. And of course, we can see that originally this triangle is only this big, but once we increase the theta, we see that this triangle also gets bigger. So theta is changing, likewise, the area of the triangle is also changing. Now the question is, how can we write an equation relating to the 5, the theta, and then the 8, and also the area? Yeah, so that's the interesting part. Well, you can quote the formula. I will write it down for you guys just to impress you guys with something. When you have two sides and the angle in between them, the area of the triangle is given by 1/2. These two sides, you multiply them, so I just put on 5 and 8, and then you multiply by sine of the angle in between them. So that's pretty much it. 1/2 times these two sides, and then times sine of the angle in between them. That's it. And I think it's also worthwhile for me to go over the proof real quick, so let me do it on the side. So suppose I have a random triangle like this, and I will just call this side A, this side B, and this is the angle in between them, which is theta. As we all know, the area of the triangle, we can say it's 1/2 base times height. Well, based on this picture, I can take the B right here to be the base, so we will have 1/2 times B. But what's the height? The height, if this is the base, I will have to draw a perpendicular line from here to here, right? And I will call this H. And now, if we look at this triangle in red, A and H and theta, the H right here is the opposite side of theta, and the A is the hypotenuse of this triangle in red. So we can use sine for this right here to connect the three variables. We know sine theta equals to H over A. And of course, we can multiply both sides by A. We get H equals to A times sine theta. And of course, that's pretty much the height. I can just put that down right here. The height is just A times sine theta. And then with that, we are done. That's how we can find the area of a triangle when we have two given sides and the angle in between them. And that's exactly what I did right here. And sometimes if you remember this formula, you can just use it right away. If not, you can just take some time to think about how you can construct the formula. Okay, so this is actually not bad at all because we have A and theta and they are both changing, so that's good. Right here, let's go ahead, multiply this out first. This is A equals to 1/2 times 40, which is just 20, and then we have sine theta. And now I can differentiate this equation with respect to time. On the left-hand side, I get the A dt. On the right-hand side, I have the 20, and the derivative of sine theta is cosine theta. But since theta is a function of time, so I will have to multiply by d theta dt. And then we're pretty much done after we plug in all the numbers and work out. We want to know dA dt. It's right here. Let's write it down. dA dt is equal to 20 is the 20 cosine, and it says we want the angle to be pi over 3. So this picture is the instance at theta equals to pi over 3, which I tried to make it 60 degrees, which I tried. Anyway, I'll just plug in pi over 3 right here. And then we also multiply by d theta dt, which is 0.06. And then just do whatever you like to do, just work it out. I will tell you dA dt, after you do all the work, you will get 0.6. In the end, let's put on the unit. Area, in this case, we have the length was meters. So the unit for area will be meters square, and the time unit was seconds, so I'll just put on meters square per second. This is positive because the area is increasing right here. So we are done. That's it. Yay, another related rates question. Here we have a balloon leaves the ground 500 feet away from the observer, and it goes up vertically at a rate of 140 feet per minute. And we would like to know at what rate is the angle of inclination of the observer's line of sight increasing at the instant when the balloon is exactly 500 feet above the observer's eyes. So, as always, let's draw two pictures to illustrate the situation. First of all, we have this person right here, and his eyes is right here, right? And then 500 feet away, that's the balloon, so I'm just going to put like this down, and this distance is always going to be 500, so let me just put that down. And then of course you have the balloon that's going up, so let me just first draw the balloon right here, and I will just label this part as the part that the balloon is going up. Well, we also want to keep track of the angle, so I'll just call this angle theta. Of course, from the eye directly to the balloon is the line of the sight, right? Okay, so this is pretty much the picture. Now, as the balloon goes up and up, we will have another picture. So here is the person again, and then this distance is still 500, and now the balloon is higher right here, and let me just put this down right here. And of course, we can label some variables if you like. You can use y because it's vertical. You can use h because it's the height maybe. I think I'll just use h. So h is changing, so that's why it's in red. This distance is always 500, so let's put that down. And even though this distance is also changing, but we don't really care because the question is only asking us to build up a connection between h and the theta. And this is the picture at the instant when the balloon is 500 feet above the ground, meaning we want h to be 500, like this. Okay, now let's go back to this, and let's just look for the information. 500 is labeled already, and it says the balloon is going up vertically at a rate of 140 feet per minute. Therefore, based on our picture and the variable, this is the h. So this right here tells us that dt is 140. So that's cool. And the question is asking us at what rate is the angle of the inclination changing, right? And the angle is getting bigger and bigger. So I'll just indicate that we want to know d theta dt is equal to what? And now let's look back to this picture. We have a right triangle, but this time I don't really care about this third side, this hypotenuse, right? Because we care about the opposite side and then the adjacent, and then also the angle right here. Opposite and adjacent, let's use tangent. From here, let me write down tangent theta is equal to h over 500. So let's put that down right here. And that's pretty much it. And we just have to remember theta and h, they are both functions of time. And right here, you can go ahead and differentiate this with respect to time. Or if you don't like the original tangent, you can actually take the inverse tangent on both sides. In fact, that's slightly easier in this situation. So let's do that. So let me just say theta is equal to the inverse tangent of this. H over 500, let me just put down 1 over 500 times h, like that. And then I will look at this and differentiate with respect to time. Because this way, on the left hand side, I get d theta dt right away. On the right hand side, the derivative of inverse tangent of something is first we put 1 over 1 plus and put on a parentheses with this inside, right? So 1 over 500 times h. And then we square that. And then we do the chain rule. We multiply by the derivative of this inside. Derivative of 1 over 500 times h. You first put down 1 over 500 and the derivative of h, because h is a function of time. We do what? dh dt So that's pretty much it, and we just have to plug in some numbers. We have d theta dt, that's equal to 1 over 1 plus 1 over 500, and the h is nicely equal to 500. So just put that in right here, and then square that, and then we have another 1 over 500 like this, and the dh dt, it was given to be 140, so we multiply by 140 right here. And then from all this, you can just work this out. This is just this computation right here. Just work everything out, and depending if you like fraction or you like decimal. If you like fraction, it's 7 over 50. Right? If you like fraction, it's going to be 7 over 50. Or if you like decimal, I'll also put that down. This is 0.14. So up to you. Anyway, I will go with decimal, and this is the theta. Theta is the angle, so I will put down radians per, the time unit was minute, so we just say radian per minute. I will box this right here for you guys. Right, so that's it.